In this section, I'd like to cover kinematic equations of motion. The last two lecture notes covered graphic analysis of motion, where we figured out displacement, change of velocity, etc. Graphically. In this lecture, I'd like to go over using kinematic equations to solve problems involving motion of objects. Now, going back to the types of graphs that we had, for example, if we know the object's velocity versus time, the object starts at certain initial velocity, so this is v initial, and then it accelerates up to a final velocity over time ti to tf. So we have some acceleration of the object. You can see that velocity final is given by velocity initial plus the slope of the straight line times tf minus ti, or in other words, velocity final is equal to velocity initial plus a delta t, where delta t is this time interval between ti and tf. And this equation here represents the first kinematic equation. However, one thing to bear in mind is that this equation is valid only and only when a is constant. So if a were not constant over the period ti to tf, you cannot use this kinematic equation. You need to break it. You need to break the interval down into segments over which acceleration remains constant. Now, the second kinematic equation relates displacement to velocity and acceleration and time interval. And we can figure that out easily by saying that, okay, if an object is moving along the x direction, the displacement is final position minus initial position, which, as we saw in the using the graphic analysis, is given as the integral of the velocity versus time plot over the interval ti to tf. And if I were to substitute for v, the velocity, this expression that we have up here, we end up with integral of ti to tf of vi plus at dt. And if you solve this integral, you'll end up with vit plus 1/2 of at squared in between the limits ti to tf, t initial to t final, i.e. xf minus xi, which is really delta x displacement, is equal to vi delta t plus 1/2 of a delta t squared, where delta t once again is tf minus ti. Okay, so that's delta t. Delta t is equal to that. And this equation here represents the second kinematic equation. This is the second kinematic equation, and once again the golden rule is that you have to make sure a is constant, that a does not change over the interval ti to tf. Otherwise, the equation is not valid. And the third kinematic equation that you get by algebraic manipulation of the first and second equations relate the final velocity squared to initial velocity squared, and acceleration and displacement xf minus xi. So this is the third kinematic equation, which does not involve delta t. And you would use the third equation, for example, if you do not have any time information. You would use the first equation if you don't have displacement or position information, you only have velocity and acceleration information. So depending on the problem, once you do your graphic representation, followed by writing down a list of all the knowns and identifying the unknowns, then you go and look at your library of equations and see which equation is going to help you in finding out the unknown of interest. So let me rewrite these equations in a neat manner if I can. I apologize for my handwriting, by the way, so I hope you get used to it as we progress in the course. A delta t, and we have x final minus x initial is equal to vi delta t plus 1/2 of a delta t squared. We have vf squared is equal to vi squared plus twice a xf minus xi. So these are the three kinematic equations of motion, and as I say, do make sure that in all three cases a is constant. We have constant acceleration, and do remember that delta t is t final minus t initial. Now the t final and my initial, they don't necessarily represent the very beginning of motion and the very end of the motion. The initial and final positions are the 2 points along the motion that you choose. You can choose anywhere in the motion to be your initial and final positions, so long as acceleration is constant over that period. Then you can go ahead and use these equations to figure out the unknowns. As an example, let us take a look at the case of, let's say, my throwing up a ball up in the air with a velocity of 10 meters per second. So let's say I'm dealing with a vertical motion, so I'm going to use my the y-axis. All right, identify the origin, the 0 point. The ball starts at 0, and I give it an initial velocity in the positive y direction, so v0 is equal to plus 10 meters per second. And the ball, by the way, there's acceleration acting on the ball is in the negative direction, and this acceleration along the y direction is minus a g, of course. It's the one acceleration due to gravity. Now the ball goes up, comes to a stop, comes back down. When it comes back down, as it happens, there's a well close by. Alright, and the ball falls into the well. This is my example, so I can be as creative as I like. And the well, let's say, is 10 meters deep. Alright, and so what we know about the knowns that we have, what we know about this scenario is that the initial position y0 is 0 meters. Okay, we know that velocity naught is plus 10 meters per second. We also know that the acceleration throughout this motion is constant. It's always minus g, no matter where in the motion we consider, so we can actually use the kinematic equations throughout the motion. So a is equal to minus g, and for the sake of this example, let's take g to be 10 meters per second squared to make our math simpler. And we know that the final y final is negative 10 meters, since the bottom of the well is minus 10 meters below the origin, which I chose to be the ground level. If we are interested in finding out, so let's say we want to find out delta t, how long is the ball in flight. Now you can choose, since acceleration is constant throughout the whole flight, you can choose your initial and final values to be any point. So it behooves you to choose your initial and final points where you have some information about the motion of the ball. So for example, we know information about this point, so I'm going to choose this as my initial point and this as my final point. Okay, if I do this, um, then you see that my y initial is 0 meters, y final is negative 10 meters, and I know my acceleration is minus 10 meters per second squared, and I also know that velocity initial is plus 10 meters per second. So notice that I have position information, acceleration, initial velocity, okay, uh, and what I need to figure out is delta t. So if I look back at the three equations of motion, it seems that since I have position information, initial velocity information, and acceleration, then the second equation is the one that is going to help me out because delta t is the only unknown in this case. So using that equation, I can rewrite y final minus y initial, that's the displacement that the object goes through, is equal to velocity initial times delta t plus 1/2 of acceleration times delta t squared. Putting in numbers, y final minus y initial is minus 10 minus 0 is equal to plus 10 times delta t, and then we have minus 1/2 times 10 delta t squared. Y minus because acceleration is minus 10 meters per second squared, which gives us minus 10 delta t plus 5 delta t squared is equal to 0. I just multiplied things through and moved things around a little bit. And this is a quadratic equation, so you use the quadratic solution to find the solution for slope. So we have a slope of, let's say, theta degrees, and we have an object which is moving down the slope. Let's say the object starts at some initial velocity. Now we know that the object is going to accelerate. Acceleration is due to gravity. However, notice that the object's motion is along the slope. So only the component of g along the motion is going to accelerate the object down in the x direction. So whenever you have a slope like this, and if there's there's exertion due to gravity acting on the ball, on the object, however, it's only the component along the motion which will contribute to the object speeding up or slowing down, for that matter. And by looking at the angles involved, you can see that this angle is also theta. So here what we have is ax, which is acceleration along the x direction. I chose my x direction at an angle. You're allowed to do that. X doesn't necessarily have to be horizontal. It behooves you to choose your x direction in the direction in which the object is moving. It makes calculating problems, the trigonometry, heck of a lot simpler. Ax is equal to, in this case it's the adjacent side, so Ax is g sine theta. And if you notice, Ax is pointing towards the positive of the x-axis, therefore it's a positive acceleration. And sure enough, we expect our object to speed up as it moves down the slope. Now if the object, we have the slope again, this is theta. um, if the object is at the bottom of the ramp and has some initial velocity and is moving it's moving up. Now in this case the direction of motion is like this, so we can go ahead and choose our x direction to be up the slope. But notice now g is still directly down, so g doesn't change, but the component of g which is along the component of g which is in the direction of x is now pointing away. So this is our ax acceleration that the object experiences due to g, is now pointing away from the positive of the axis, which means that ax is equal to negative g sine theta. This angle is still theta, and the magnitude of ax is still given by g sine theta, but because the acceleration is pointing away from the positive of the axis, we have a negative acceleration, and sure enough we would expect the object to slow down as it moves up the slope. Okay, so identifying these similar triangles is an important part in solving motion problems. So if we have an object which is moving up, this is a numeric example, so this is a 10-degree slope. We have an object with let's say 10 meter per second initial velocity, so vi is 10 meters per second. How far would the object move up the slope before it comes to rest? When it comes to rest, of course, v final is 0 meters per second. So we're interested in how far up the slope will it move. So we're interested in if this is well, let me draw the axis. So I'm going to choose my x direction to be up the slope. The acceleration due to gravity always points down, which means that the component of acceleration along the motion is now pointing away from the positive of the axis. My ax is given by negative g sine of 10 degrees, and I'm interested in the displacement, so this position I call x initial, this is my x final. And if you so the information that I have, I know my x initial is 0 meters, x final is what I'm trying to figure out. I know my acceleration, and I have velocity initial, which is, velocity initial is plus 10 meters per second because it's pointing towards the positive of the axis, and I also have final velocity information, which is 0 meters per second. So having these knowns, and I'm interested in finding final xf, is the third equation which is of most help, which is relates final velocity squared to initial velocity squared plus twice acceleration times displacement. Plugging in numbers, we have 0 is equal to vi squared is 100 plus 2, acceleration is minus g sine of 10 degrees, and the displacement is xf minus 0 because xi is 0. I chose xi to be 0. So you see that in this equation, g we know, of course, 9.81. xf is the only unknown which you can go ahead and solve for to figure out how long an object would move up the slope under these conditions. Please read through chapter 2. Chapter 2 is full of useful examples, and I will be posting the notes for chapter 3, which is vector algebra, sometime early next week. And look for homework assignment 2, which should be due towards the middle of next week, actually Wednesday, hopefully, which will include problems out of chapter 2.